Okay, let's dive right into this explainer and see exactly how the immutable, absolute laws of orbital physics are dictating not just our deep space future, but the entirely new realities of geopolitical strategy. We are witnessing this incredible moment in history right now where our reach into the cosmos is expanding faster than ever before. But, along with all that progress comes some incredibly complex challenges that we really need to unpack. And it all kind of boils down to this. How do you actually win a war in a domain where firing a single shot could literally destroy the entire battlefield? To answer that critical question, we have to understand just how fragile near-Earth orbit actually is, and we need to look at the massive, mind-blowing vehicles currently being built to dominate it. Because space, it's not like a traditional battlefield on land or out at sea. It's an environment so delicately balanced that the sheer act of fighting in it could render it completely unusable for everyone, potentially for generations. Here is our roadmap for today's explainer. We'll quickly cover the rules of orbit, move into the Upmass Advantage, examine the Starship Solution, look at in-orbit refueling, and finally face the realities of the orbital battlefield. Let's start with Section 1, the rules of orbit. Space really isn't just a place you go, it's a harsh environment governed by incredibly strict physics. And the most important rule to understand is the concept of delta V. Delta V is basically the ultimate currency of space. Think of it not as miles traveled, but as the raw energy you have to spend to change your speed. It takes a massive 9.4 kilometers per second of delta V just to escape Earth's gravity well and reach low Earth orbit. But here's where it gets really fascinating. It reveals this totally counterintuitive truth. Energetically speaking, a satellite sitting all the way on the surface of Mars is actually just as close to low Earth orbit as a fully fueled satellite sitting right here on a launch pad on Earth. Up there, distance means very little. Energy is literally everything. So the crucial point we have to keep in mind is that while physical space seems infinitely large, it's space, right? Operational space is actually shockingly tiny. Take geostationary orbit, for example. It's effectively just a single, one-dimensional ring right around the Earth's equator. And low Earth orbit? It's basically a highly structured highway system. Satellites need very distinct swim lanes just to avoid smashing into each other. Add in the limited radio frequency spectrum available to transmit data back down to us, and you quickly realize that prime orbital real estate is highly congested and deeply, deeply valuable. Which brings us to Section 2, the Upmass Advantage. Because escaping gravity takes so much of that energy we just talked about, the sheer ability to lift heavy things into space, which the industry calls upmass, becomes your ultimate strategic bottleneck. Just look at the stark contrast in daily upmass capabilities projected for global powers in 2025. You have the United States at 9.3 tons a day, compared to 1.8 tons for China, and a mere 0.4 tons for Russia. This massive, game-changing disparity is largely driven by the American commercial sector's rapid transition to reusable rockets. Because when you can just land and reuse the rocket, you dramatically lower the cost, and your launch frequency goes through the roof. So why does having all that upmass matter so much? Well, if you can haul the most weight up there, you can literally spend that weight on better survivability. You can slap heavier shielding onto your satellites to protect against debris. You can carry way more propellant so you can actively maneuver out of the way of threats or track adversaries. You can build these massive multi-orbit constellations. And most importantly, if you lose a satellite during a conflict, you have the launch capacity to just rapidly replace it. Basically, upmass equals overwhelming operational scale. Let's look at how this scales up in Section 3, the Starship Solution. SpaceX's fully reusable Starship is stepping in to completely rewrite these orbital economics. Its iterative design is scaling up payload capacity to a degree that is just unprecedented. We're going from 15 tons in Block 1 all the way up to an expected 200 tons in Block 4. That is 440,000 pounds of payload hauled up to low Earth orbit in a single launch. That shifts us entirely away from these fragile, weight-constrained satellites we've used for decades into an era of massive, heavily armored, and heavily fueled orbital assets. It's a total paradigm shift. And to physically lift that much steel and cargo, you need an insane amount of power, specifically 33 sub-cooled liquid methane and oxygen Raptor engines strapped to the bottom of the Super Heavy booster. In later blocks, those engines are going to generate an immense 22.1 million pounds of thrust. Just to put that into perspective for you, that is literally more than double the thrust of the mighty Saturn V rocket that took the Apollo astronauts to the moon. Absolutely wild. But what goes up has to come down safely if you want to reuse it, right? Returning that massive upper stage through the atmosphere requires bleeding off all that incredible orbital energy. And they achieve this using roughly 18,000 hexagonal heat shield tiles, which altogether total over 20 cubic meters of volume. It is just a stunning feat of engineering, all designed around one single driving goal: rapid and total reusability. All right, moving on to Section 4, in-orbit refueling. Let's talk about deep space gas stations. You see, Starship isn't designed to just hang out in low Earth orbit, but pushing those massive payloads out to the Moon or Mars, that demands a deeply complex maneuver. Slated for demonstration in 2026, this whole highly technical process involves first launching a propellant depot into orbit and then launching tanker starships that fly up and dock with it. Using a pressure differential, they transfer super-chilled cryogenic liquids between two massive vehicles that are hurtling around the Earth at 17,000 miles per hour. Then the tanker undocks, re-enters, and lands. And make no mistake, this refueling architecture is the absolute linchpin for NASA's Artemis program. To put it in perspective, it's going to take approximately 10 tanker launches just to fill up a single Starship human landing system so it has enough juice for its lunar journey. It's an incredibly complex logistical chain, sure, but once we master it, it literally opens up the entire solar system for us. Which brings us to the geopolitical reality in Section 5, the Orbital Battlefield. All this physics, upmass, and engineering we've just covered, it's setting the ground rules for modern military strategy. Historically, nations built what's called exquisite architectures. These were a few billion-dollar bus-sized satellites that could do absolutely everything, but man, they were incredibly vulnerable to just a single strike. Now, because of these high upmass capabilities, nations are sprinting toward proliferated architectures. We're talking thousands of disaggregated, replaceable, single-mission satellites. It's like a giant swarm. If an adversary takes out 10 of them, who cares? The network completely survives. And right now, as we speak, nations are locked in a Cold War using what are known as gray zone tactics. Every single day, we're seeing interference with commercial and military signals, things like GPS jamming, radio frequency spoofing, cyber attacks, and even using ground-based lasers to temporarily blind optical sensors on satellites. These tactics are favored because they allow rivals to mess with each other and disrupt operations without actually crossing that very dangerous line into a kinetic physical destruction. But let's be clear, the capability for physical destruction is absolutely there. In fact, physical anti-satellite or ASAT weapon testing has been happening for decades. The US struck its own SolWind satellite way back in 1985. Russia conducted a kinetic test in 2021, and China did the same in 2023. These tests prove unequivocally that all the major global players already possess the terrifying capability to obliterate targets right out of orbit. Here's the catch, though. A kinetic strike in space isn't like dropping a bomb on Earth. Up there, it causes cascading fields of debris. As U.S. Space Force General Chance Saltzman pointed out, applying traditional destructive military force in space actually threatens all assets, regardless of whose flag is painted on the side. A single explosion introduces thousands of new, completely untrackable projectiles into orbit. Meaning, in a full-scale space war, a single shot could literally trigger a chain reaction that renders the entire domain usable for everyone, friend, foe, and commercial operator alike. So that leaves us at a pretty profound crossroads. As we master these complex orbital constraints with staggering engineering feats like Starship, we're left with a massive question to ponder. Will our newfound ability to launch thousands of tons into orbit bring stability and resilience to the domain, or will it just spark a massive conflict that pollutes near-Earth space and denies us the stars forever? It's a lot to think about. Thanks so much for joining me on this explainer, and I'll catch you next time.